Aloha BIOCHEM. In this third lecture on Chapter 5, we discuss molar mass calculations. So in this video, we'll cover sections 5.5 and 5.6 on the mole and molar mass calculations. You may have heard of the mole before. The mole, or 1 mole, is equal to the number 6.022 times 10 to the 23rd. So this is a very large number, and chemists use this all the time. In fact, this is what we count by in chemistry. Just as a baker counts by the dozen, the chemists count by the mole. Now this number is called Avogadro's number, and it's named after the Italian physicist Amedeo Avogadro, who lived from 1776 to 1856. Here's a picture of Avogadro. He's an interesting looking chap, and he seems to watch you no matter where you stand. That eye of his seems to follow you. Now, the reason the number is this, and it's not something else, is because of the way it was defined. It's defined to be the number of atoms in exactly 12 grams of carbon-12 isotope. So imagine you have some carbon, and you filter out all of the carbon-13 isotope, and all you have left is the carbon-12. And you measure out 12 grams of that, and then count how many atoms there are. And I imagine Avogadro doing this, maybe with a pair of tweezers and a beaker. He counts them, picks them up one at a time. Plink, 1, plink, 2, plink, 3. And if he keeps doing this and doesn't lose count, then eventually, after eons and eons, he'll get to the last one, and that will be how many there are. Now, of course, it was measured using a much more convenient approach than that, and Avogadro wasn't even the one to do it. The number was defined much later than Avogadro's life in the 20th century. But this is the number, and we use it all the time, and it's what we count by in chemistry. So if you have a mole of something, then that's how many you have. For example, a mole of hydrogen equals Avogadro's number of atoms of hydrogen. A mole of water is Avogadro's number of molecules of water. And a mole of sodium chloride is Avogadro's number of formula units of sodium chloride. Remember, sodium chloride is not made of molecules, it's an ionic compound. And so if you have one sodium cation and one chloride anion, together they make up what's called a formula unit. The number is also seen in the relation between grams and atomic mass units. If you recall back to Chapter 1 when we were doing unit conversions and converting between different mass units, we did see the atomic mass unit back then, and 1 gram is equal to Avogadro's number of atomic mass units. That's how the atomic mass unit was defined. Now in this chapter, we deal with the mole quite a bit, and we're mostly interested in how much a mole of a substance weighs. If you look up elements on the periodic table, that information, the weight of a mole of an element, is actually contained right on the periodic table. So looking up hydrogen, for example, I'll show you hydrogen here. It's element number 1. Its atomic number is 1, and its atomic mass is 1.008. Now, in Chapter 2, we interpreted the number to be the atomic mass, but it actually has 2 interpretations. Let's recall from Chapter 2 that we interpreted it as the atomic mass, and so 1 atom of hydrogen weighs 1.008 atomic mass units. Now, of course, no particular hydrogen atom actually weighs that much, because hydrogen atoms are either H1 or H2 isotopes. So they weigh close to 1 atomic mass unit or close to 2. But the average hydrogen atom weighs that much. And that's because there's more abundance of the H1 isotope. So just like the average American family has 2.5 kids, no American family has that many. They either have 1, 2, 3, or 4, but the average family has 2.5, and the average hydrogen atom weighs that many atomic mass units. Now, the second interpretation of this number is that it tells us how heavy a mole of hydrogen atoms weighs. 1 mole of hydrogen weighs 1.008 grams. Now, that is not a coincidence. In fact, it's a direct result of the way we defined the atomic mass unit. So if you accept that an atom of hydrogen weighs 1.008 atomic mass units, and you use the relation between grams and atomic mass units, then you can, derive the second interpretation. So using the first one and the definition of AMUs, you get the second interpretation, which tells you how heavy a mole is. So let's just see how this is done real quick. First of all, we know that 1 mole of hydrogen is Avogadro's number of atoms of hydrogen. Okay, that's the definition of a mole. And 1 atom of hydrogen is 1.008 atomic mass units, the average atom. And then finally, the relation up here tells us that Avogadro's number of atomic mass units equals a gram. So this is how we figure out how heavy a mole is right here, doing the calculation. We take 1 mole of hydrogen, and using the first relation, we convert moles to atoms. And the mole units cancel. And then using the second relation, we convert atoms to atomic mass units, and the atom units cancel. And the third relation gets us from atomic mass units to grams, and the atomic mass units cancel, and we're left with units of grams. So you see, we've converted from moles to grams, and doing the calculation, you see that it involves a bunch of ones, and also Avogadro's number actually cancels off, and you're left with simply 1.008 grams. Now this works for every single element. So not only does 1 mole of hydrogen weigh 1.008 grams, but if you look up any other element on the periodic table, you can quickly determine how much 1 mole of it weighs. So for example, looking up the element carbon, carbon's atomic mass is 12.011. So 1 atom of carbon weighs 12.001 AMUs, and a mole of carbon is 12.011 grams. And you can do that for any other element on the periodic table. It's very useful that we can use that number in both ways. Okay, the weight of an atom or the weight of a mole. Now, in chemistry, we deal with substances and compounds, and so we're more interested in the weight of molecules and the weight of moles of compounds. So let's talk about the relation between molecular weight and molar weight for substances. And as an example, let's calculate the mass of 1 molecule of water and also 1 mole of water. First, a molecule. If you have a molecule of water, here it is, here's its Lewis structure. You can see that the molecule contains 2 hydrogen atoms and 1 oxygen atom. So to calculate the mass of a molecule, you need to add the mass of the 2 hydrogen atoms, okay, and the mass of 1 oxygen atom. Well, we get that information right on the periodic table. Remember, the periodic table tells us how heavy atoms are. And so, 2 hydrogen atoms, let's look up hydrogen again. It's element number 1, and its atomic mass is 1.008 atomic mass units. You remember, if you're dealing with a small atom, you use the small units. Okay, so you got 2 of them, you multiply that by 2. You got 1 oxygen atom in the molecule, so 1 times the atomic mass of oxygen, and oxygen's over here, so that's 1 times 15.999. And so there you go, you got 2 hydrogens and 1 oxygen. If you sum that up, you get 18.015 atomic mass units, and that's the weight of a water molecule. Now, again, due to isotopes, no particular water molecule actually weighs this much. After all, some of them will have the H1 isotope in there, and some of them have the H2 isotope, but this represents the mass of an average water molecule. We call this the molecular weight of water. Now, what about the mass of 1 mole of water? So imagine a mole of water molecules, Avogadro's number of water molecules. And say, let's line them up all in a row, starting with the first one and the second one all the way up to the last one. So there is a mole of water molecules. Now, each water molecule contains 2 hydrogen atoms. So if you have a mole of molecules, then you got twice that many hydrogen atoms. You got 2 moles of hydrogen. And each molecule contains 1 oxygen, and so a mole of them would mean you also have a mole of oxygens. So to calculate the mass of the entire mole, you add up the mass of the 2 moles of hydrogen plus the 1 mole of oxygen. And you remember the periodic table also tells us how heavy moles of the elements are. Okay, so you got 2 moles of hydrogen and 1 mole of oxygen. So, going back to the periodic table, we shouldn't need to go back, but just to verify, there's hydrogen's mass right there. So 1 atom is that many atomic mass units, and 1 mole is that many grams. And the same thing for oxygen, of course. Oxygen, 1 mole is that many grams. And so multiplying the molar mass of the elements by how many atoms are in the formula, you got 2 hydrogens and 1 oxygen, and then adding that up, of course, you're going to get the same answer as before. So 18.015, and this time we call that molar mass because it's 18.015 grams. So the mole, you get the larger unit of grams. The molecule, you get the smaller unit of AMU. Now this can be done for any other compound. If you know the chemical formula, you simply look up all of its elements on the periodic table. Make sure you multiply them by how many atoms are in the formula, and then add it all up, and that'll get you the molar mass. So here's an interesting example of a few different substances for which that was done. Here's water. So 1 mole of water molecules is 18.02 grams. So we say 18.02 grams per mole. Now that's what a mole of water looks like. It's about 18 milliliters. Because remember, the density is 1 gram per milliliter. So if you have 18 grams, you got about 18 milliliters. So there you go. That's a mole of water right there. Now, a mole of sodium chloride is pictured right here, and its molar mass is 58.44 grams per mole. So looking up sodium on the periodic table, and chlorine, you got 1 sodium and 1 chlorine. And sodium is right here at 22.99, and chlorine is over there at 35.45. So adding up 1 of each, you get 58.44 grams per mole. And that's a mole of sodium chloride pictured right there in that weighing dish. Now here's a mole of sucrose. That's quite a bit. And the reason a mole of sucrose is so much is because its chemical formula has a lot of atoms in there. It's C12H22O11. So if you add up 12 carbons, 22 hydrogens, and 11 oxygens, you'll get 342.3 grams per mole. So sucrose molecules are quite heavy, and so if you have a mole of them, you got a lot of stuff there. It's a pretty interesting picture to compare, moles of different substances here. So let's do a few calculations involving the molar mass. In the first example, we're asked how many water molecules is 10 grams. Now, to convert mass of a substance to the number of molecules of that substance, we need certain relations. And so let's just list the relations that we have learned about water. First of all, the molar mass of water tells us that 1 mole of it equals 18.015 grams. And Avogadro's number, don't forget that, 1 mole of water is 6.022 times 10 to the 23rd molecules of water. From the definition of atomic mass units, we know that a gram of water is equal to 6.022 times 10 to the 23rd atomic mass units of water. It's just 2 ways to express the mass of water. And the molecular weight of water, so a molecule, equals 18.015 atomic mass units. Now, using these 4 relations, we need to somehow connect grams with water molecules. And if you look at them, and you look closely at the first 2, you can use the first one to get from grams to moles, and then the second one to get from moles to molecules. So we can answer this question with these first 2 relations. Now, there's also another way to do it, using the third and the fourth relation. So going from grams to molecules again, we can use the definition of AMU here to go from grams to AMUs, and then the molecular weight to go from AMUs to molecules. So that's another way to do the connection. So let's just go ahead and do the calculation using both methods, using the first 2 relations and then the second 2 relations as well. Using the first 2 relations, we start with our 10 grams, and then the molar mass of water gets us from grams to moles, and then Avogadro's number gets us from moles to molecules. You can see the gram units canceling and the mole units canceling, and you're left with molecules. And doing the calculation, 10 over 18.015 times Avogadro's number gets you 3.342 times 10 to the 23rd. This rounds to 3.34 because we started with 3 sig figs for the mass. So 3.34 times 10 to the 23rd molecules. Now, using the third and the fourth relations should get us the same answer, because it's, we're being asked the same question again. So starting with our 10 grams of water, the third relation will convert from grams to atomic mass units. So we're just getting to a different unit of mass here. The gram units cancel. And then the fourth relation for the molecular weight gets us from atomic mass units to molecules. And the atomic mass units cancel, and we're left with molecules again. And you can see that the calculation of the numbers is actually the same. 10 over 18.015, you can do them in any order, over 18.015 times Avogadro's number, and that's exactly what we did up here, and so we get the same answer, of course. Here's another example, a little bit more involved. A dietary supplement provides 175 milligrams of calcium hydrogen phosphate. That's CaHPO4 per pill. The question asks how many moles of calcium hydrogen phosphate are in the pill. And then we're also asked how many moles of calcium are in the pill and how many milligrams of calcium are in the pill. I'll show you a picture of this supplement here. you go. It's called Bone Care because it contains calcium and phosphorus, which are good for your bones. And looking at the back label, you see, along with some other things, dicalcium phosphate. Here they call it dicalcium phosphate. We'll call it calcium hydrogen phosphate, which is the appropriate name. And the amount per serving is 350 milligrams, but we see that the serving size is 2 pills, okay, 2 capsules. So each one contains 175. And so, each pill contains 175 milligrams of the substance. And let's go through let's answer the first question. How many moles of calcium hydrogen phosphate are in the pill? Now, to get from the mass of calcium hydrogen phosphate to the number of moles of it, we're going to need the molar mass again. To calculate the molar mass of CaHPO4, we look up these 4 elements on the periodic table and multiplying their respective atomic masses by how many atoms are in the formula, and then adding them all up, we should have the molar mass. So let's just verify that these are the correct numbers, looking up calcium. Calcium is over here, one of the metals, and 40.078. And hydrogen is a 1.008. And then next is phosphorus, that's 30.974. And then we have oxygen at 15.999. So they all are correct. And multiplying them by the number of atoms in the formula, you got 4 oxygen, so multiply that one by 4, the rest are 1. Then adding them all up, you get 136.056. Now this number tells us how heavy a formula unit is, and it also tells us how heavy a mole is. And so we'll use the molar interpretation. 1 mole of CaHPO4 equals 136.056 grams. Now, to get to, since we're starting with milligrams, we're also going to need the conversion between milligrams and grams. Okay, so if we start with milligrams, we can go from milligrams to grams using the milligram to gram conversion, and then we can go from grams to moles using the molar mass conversion. And here's how you do it. Starting with 175 milligrams of CaHPO4, you go from milligrams to grams, and then you go from grams to moles. You see the units canceling, and you're left with moles of the substance. And doing the calculation, you get 0.001286 moles. It'll round to 0.00129 because we're starting with the 3 sig fig number. And so that answers the first question. How many moles of the substance are in the pill? The next question asks how many moles of calcium are in the pill. Now we've already figured out how many moles of this formula unit are in the pill, and it should be pretty easy now to figure out, using that, how many moles of calcium are in the pill. Now each formula unit contains 1 calcium. So if you have a mole of the formula units, then you have a mole of calciums. And so this next one will be a trivial calculation, starting with the number of moles of the substance. Okay, we copy that number, the unrounded number again over, and we convert from moles of calcium hydrogen phosphate to moles of calcium. 1 mole of it contains 1 mole of calcium, and so we're left with the same number as before. Okay, there's 1 calcium per formula unit, so it's equal. Now, the last question asks, how many milligrams of calcium are in the pill? Now, to get milligrams from moles, now that we know how many moles of calcium there are, we should be able to convert that to mass using the molar mass of calcium. So looking up calcium again on the periodic table, okay, it's still 40.078, And so 1 mole of calcium is 40.078 grams. And so there you go. We've written down the molar mass of the element calcium right there in that last relation. And so this will get us from moles to grams of calcium. And then using the milligram conversion again, we can get from grams to milligrams. So let's take our moles of calcium that we've already figured out, turn our moles into grams using the molar mass of calcium, and then go from grams to milligrams using the milligram conversion. You see the units canceling again, and we're left with milligrams of calcium, and the calculation gets us 51.54 milligrams of calcium. That's 51.5 milligrams of calcium. So a pretty involved problem there. You got 3 questions in one, but a typical molar mass calculation. In our last example, we're asked how many molecules of ascorbic acid, that's vitamin C, are in a tablet containing 1,000 milligrams. So you're given the mass of vitamin C, and it's in a tablet, and you're asked how many molecules of vitamin C are in that tablet. Okay, starting from mass, determine the number of molecules. Now, here's a picture of vitamin C's structure, and you're given the chemical formula, C6H8O6, but you should be able to figure that out from the structure. You can see the 6 oxygens, of course, 1, 2, 3, 4, 5, 6. The carbons are at the vertexes. You got 1, 2, 3, 4, 5, 6. And then the hydrogens are you got 4 of them shown because they're attached to oxygen. So you got 1, 2, 3, 4. But then you got 2 more here, because there are only 2 bonds. So the other 2 go to hydrogens. So that would make 6, and then 7, 8. So there's the formula for ascorbic acid. Now, if you have the mass of ascorbic acid and you're asked to calculate the molecules, you're going to need the molar mass conversion again. That relates grams to moles. Okay, and if you know how many moles, you can figure out how many molecules. So let's get the molar mass using that formula. Looking up the atomic mass of carbon, hydrogen, and oxygen, there they are, 12.011, 1.008, and 15.999. Okay, you got 6 carbons, so that's 6 times that, and then 8 hydrogens, and 6 oxygens, and then multiplying them, and then adding it all up, you get 176.124. So this number, of course, tells us how heavy a molecule is, and it also tells us how heavy a mole is. So a molecule is 176.124 AMUs, and a mole is 176.124 grams. Okay, we're starting with the mass in units related to grams, so this is going to be the one we want. Now, we also need the milligram conversion again, so a milligram, 1,000 of them equals a gram. And then we're getting to molecules, so we need Avogadro's conversion again. 1 mole is Avogadro's number of molecules. Now, starting with the number of milligrams, we use this one to get to grams, use the molar mass to get from grams to moles, and then Avogadro's conversion to get from moles to molecules. Putting it all together, you can see how it's done here. 1,000 milligrams, go from milligrams to grams, grams to moles, and then moles to molecules. And you can check the units do cancel off, and you're left with molecules. And the numbers, 1,000 cancels 1,000, that's nice. And you got Avogadro's number over the 176.124, and that's 3.419 times 10 to the 21 molecules. It's quite a lot of molecules there. So these are some typical calculations involving molar masses, and if you're able to follow these and you're doing pretty good, and you should be able to apply the same methods for any other substance if you know its chemical formula. In our next lecture, we're going to use these techniques to do calculations involving chemical reactions, and so stay tuned for calculations of involving chemical equations. Aloha.